In this lecture, let us talk about noise in AM system with carrier. So the receiver that we are going to consider is an envelope detector. So the process is very similar to that of synchronous demodulator. So let me start with the received signal. So it is A plus m of t multiplied by cos of omega ct. Here, look at here, I did not use any constant. Okay, notice that. So don't get confused by the fact that sometimes I use some factor and sometimes I do not use some factor. So it would be absolutely no difference to the final result. So please be clear about that. So now how should I proceed? Before actually proceed, let me see, you can give me, okay, let me see, we can get some idea. Let us do some simple calculations. Very briefly, what should be the process now? Because at the receiver we are not going to multiply this cos omega ct or root 2 cos omega ct. We have to do envelope detector. So what kind of mathematics should we do now? So the output of the envelope detector is the envelope of the modulated signal. Envelope detector input is modulated signal and the output is envelope of the modulated signal. Okay, so the actual received signal, let me say yi of t, has signal part plus noise part. So it could be the envelope of signal plus noise. Okay, so this is my envelope detector. Before, let me draw the figure. A plus m of t cos omega ct, this is coming, and the noise is added here, n of t. After that, you put a band pass filter to separate out the signal which you want. Let me say this is my y of t, and this y of t is given to the envelope detector, and this is output of the envelope detector. So we need to find out Si, Ni and S naught, N naught. Now what is your yi of t? Yi of t is the signal part, A plus m of t times cos omega ct, plus the noise is n of t is passing through this band pass filter. So it becomes, in this point it becomes your narrow band noise, Ni of t. So we know how to represent the narrow band noise. So before the band pass filter, it is white Gaussian noise, right? And in this point it becomes narrow band Gaussian noise. Okay, remember when I say the input to the demodulator, we are considering output of the band pass filter, which is the front end or the first stage of the receiver, because the other channels also will come into your demodulator. So the receiver will always associated with the band pass filter to pick up the desired signal with the bandwidth of B hertz in the case of SSB or 2 B hertz in the case of AM system. Like if I draw, this is FC and this is minus FC, 0 like this. So this is my band pass filter, ideal band pass filter characteristics. So what is the bandwidth here? 2 B hertz. And the negative frequency side, again you have 2 B hertz. Okay, here we have the bandwidth of 2 B hertz. So Ni of t you can write in terms of quadrature representation, that we know how to write. So let me write down now, A plus m of t multiplied by cos of omega ct plus this quadrature representation is Nc of t cos omega ct plus ns of t sin omega ct. Okay, now combine the in phase components and quadrature phase components. See, these are in phase components and this is quadrature phase component. So combine these two guys together, then a plus m of t plus n suffix c of t multiplied by cos omega ct plus the quadrature component ns of t sin of omega ct. This is my received signal which is given to the demodulator, I mean envelope detector. Now let us write down the expression for your signal component. Okay, so what is the signal component? This is my signal part. Okay, so signal, input signal is equal to a plus m of t times cos of omega ct. What is the power in it? This we already calculated. Okay, so this is going to be a square plus m square bar by 2. Same calculation, you can do it. Okay, straight away wrote. Say this is a expected value of a plus m of t whole square and expected value of this. And if we expand this, then it is a of a square plus m square of t plus 2 times a times m of t. So you take expectation inside, you will get the expected a square plus expected value of m square of t plus 2 times a is constant, you can pull out of expectation m of t, and this a square is again expected value of a square is a squared plus this is m squared of t whole bar expectation plus 2a m of t and whole bar. And what is this? Don't we say this is a mean value, and we assume that m of t is 0 mean void sense stationary process. Therefore, this term will be 0. So this is what you left with. And of course, in the denominator I forgot to put 2. Okay, so 2 will come in the denominator by 2 here, and the whole thing will be divided by 2. So if you calculate, the 2 factor will come. Because I don't have the root 2 factor here, then it will be a square plus m square of t by 2. Because that cos term I did not consider. If you consider cos square, then it becomes cos square omega ct. Because in fact, if you put this, then you remove this guy, you put cos square omega ct, and then this cos square omega ct becomes 1 plus cos 2 omega ct. So that 1 you multiply here. It's very simple actually. Maybe because that cos term I did not consider in this. So expected value of a plus m of t times cos of omega ct. Okay, and square, this whole thing will be squared. So this is going to be cos square becomes 1 plus cos 2 theta a plus m of t the whole square times it is cos squared of omega ct, and this cos squared omega ct becomes 1 plus cos 2 omega ct by 2, and this is multiplied by a plus m of t the whole square. And again you do the same process. Finally you will end up with a squared plus m square by 2. Okay, so that is the expression for the input signal power SI. Then my yi of t, I have in phase component and quadrature phase component. So this I can write in terms of envelope and phase. Why do I need to write in like that? Because I am going to give this signal to the envelope detector. So I need to know what is the envelope. So let me write down that in that envelope mathematically. So yi of t is equal to envelope, let me say ei of t times cos of omega ct plus theta of t. Okay, I can always write in this form using trigonometric expression, where ei of t denotes the envelope of let me say this is what should I give this one? Okay, let me call equation 1 and this one equation 2. So equation 1 can always be written in terms of equation 2. Therefore ei of t is defined as envelope. This envelope is equal to square root of the in phase component square plus quadrature component. Maybe I'll write down here. What is the in phase component? This guy. This is my in phase component. So a plus m of t plus nc of t the whole squared plus the quadrature component. What is the quadrature component? The quadrature component is ns of t, ns squared of t. That's it. This is a of t, and the phase angle theta of t is equal to tan inverse of the quadrature component ns of t divided by in phase component a plus m of t plus nc of t. Okay, but this phase angle is not important for us because our envelope detector will least bother about that. Okay, so therefore the phase angle is not of interest to us, because finally the envelope detector will produce an output which is proportional to the envelope. So the phase detector will not depend on the angle of the signal, this phase angle. So this is the main thing of interest to us. The envelope is the main thing for us, and the envelope contains, as you can see, the signal part m of t as well as some noise part n of t. This is my signal part and this is my noise part, but there is a non-linear dependence now. Okay, and that's what makes the situation in general a little more difficult. So this is not that much easy to analyze compared to your SSB, DSB, SE and then AM with synchronous demodulation. So because it is a non-linear relationship. So to simplify the situation, one makes some assumptions, and the usual assumption that you can make to do the initial analysis is small noise assumption and a large noise assumption. Now first let us consider small noise condition. Case 1. Small noise assumption means that the noise level is smaller than the signal amplitude. Essentially to say that the signal power at the input is much greater than the noise power. Okay, so input power SI is much greater than the noise power, input noise power to the detector. That means what? The signal is much stronger than the noise. What is your input to the signal, input signal to the detector? It is A plus m of t multiplied by cos omega ct plus ni of t, and this part is signal part and this is my noise. So the signal is much stronger than the noise, much stronger than the noise. And particularly this kind of assumption depends on the kind of situations you are working with. Okay, sometimes your receiver is very close to the transmitter and sometimes you may be very far away from the transmitter, right? So we don't know. So let us assume here the signal is stronger than the noise. Typically in broadcast application it is justified because you have to maintain a good SNR, otherwise you cannot receive. In many other applications it may not be justified, but in broadcast applications it is justified. So in that case if you apply small noise assumptions, then we can simplify the above expressions. Okay. In case if the signal strength is much less than noise, then you have to consider large noise assumption, that's it. Okay, otherwise you have to write a general expression which is very complicated. So in order to simplify things and to give some kind of understanding, it is convenient to make these assumptions like small noise assumptions and large noise assumptions. Now let us consider small noise assumptions, and then we will move on to large noise assumption. So the small noise assumption will imply here, that means A plus M of t is much greater than Ni of t for all the time. So this is a condition for small noise assumption. Okay, although this Ni of t is actually random, making this kind of statement is a kind of loose statement, but I think at this stage it is convenient to make this kind of loose statement. That's why we put for all time. Okay, this will of course also imply the following, like A plus M of t is much greater than Nc of t. Similarly, A plus M of t is much greater than Ns of t for all time, for all t, because Ni of t is after all the in-phase component and quadrature phase component. If this is the condition, then your envelope will be simplifies as follows. What is your envelope? R of t is equal to square root of A plus M of t plus Nc of t whole square plus N squared of t. Now if you make this assumption, then you can disregard this guy. Therefore your R of t for A plus M of t is much greater than Ns of t, then this implies your R of t is equal to A plus M of t plus Nc of t. Okay, this is my envelope. Instead of now I am using different notation. Let me use Ei of t, and because initially I defined envelope is Ei of t, not R of t. And of course this one is blocked by some capacitor. Capacitor will block this guy in the envelope detector. Okay, so we are not interested in A, we are only interested in M of t. So the useful signal power at the output is, my signal will be only M of t. Therefore signal power at the output of the detector S naught is equal to M square of t bar. And what is the corresponding noise power? Noise power N naught is equal to Nc squared of t. And how much will it be? Again this is, remember this is an AM signal whose bandwidth is 2B. Okay, so this is Fc, and in the negative side I also minus Fc. Here also the bandwidth is 2B, and here also the bandwidth is 2B. Therefore here the noise power is Nb, and here the noise power Nb. Total noise power is 2Nb. So in this case the total noise power is 2Nb. So therefore Nc squared of t is equal to 2Nb. So same picture as before, so nothing has changed, things are absolutely the same as before. Therefore S naught by n naught is equal to m square of t divided by 2nb. Now let us write in terms of our benchmark gamma. So for that, what you do, m square of t bar divided by 2nb, multiply both the numerator and denominator by input power si and si. What is si? Si is, just now we got, where is it? Yeah, a square plus m square bar by 2. So substitute that here. So before that, let me rearrange this equation. Si by nb, right? Plus m square of t bar divided by 2 times si. Can I write like this? Yes. And what about this guy? This is our friend benchmark gamma times m square bar of t divided by, what is si? Si is a squared plus m squared by 2, and this whole thing is multiplied by 2, this 2, and so the 2 and 2 will get cancelled. So this is gamma times m squared by a square plus m squared. This is my s naught by n naught. So you left with the same expression as before. So the output SNR is, or you can write m squared bar by a squared plus m squared bar times gamma. So whatever the expression we got for synchronous demodulator, the same expression we are getting here. So this is very, very important to appreciate. Although the expression is same, but there is a very, very important message here. Okay, so this is for envelope detector. Output SNR of envelope detector. Similarly, we also got the same expression s naught by n naught is m square bar divided by a square plus m square bar times gamma for whom? Synchronous detector. But there is a very, very important difference between these two guys. Even though the expression is same expression, but very, very important point. Here in this envelope detector and synchronous demodulator, the output SNR is exactly the same. Okay, there is no difference. But there is one small important difference. What is the difference? In the synchronous detector, the output SNR is the expression. This expression is valid irrespective of noise condition. Irrespective of the input SNR. But this guy is valid only large signal condition. Okay, so in the envelope detector we assumed this large signal condition. Okay, the noise is much less than the strength of the signal is much larger than the strength of the noise. But in the synchronous detector, it doesn't matter whether the signal strength is low or the noise strength is high, doesn't matter. Whatever it is, it gives this kind of performance. Therefore, your synchronous demodulator is much better than your envelope detector. Okay, so all we are saying is that this assumption that we made in the analysis is not valid, and therefore this expression will not be valid under large noise condition. You will not be able to calculate the output SNR using this expression. That's all we can say. Whether it is worse or better, we don't know. So we have to find out. Basically what we are saying is, in high SNR situations it hardly matters. Okay, this expression is very good in high SNR situations. And it is not good for if we cannot use under low SNR condition. So basically what we are saying is, in high SNR situations it hardly matters. Okay, you can use that. We don't lose any further information in terms of power efficiency if you use envelope detector rather than the synchronous detector. But in the high SNR situation there is no loss. So even you just go out and use the envelope detector without even thinking twice, because you will not lose any performance. But for low SNR situation, the envelope detector actually very bad. So I must a little more careful about that. Although it is not obvious, but that is the very important point that one should be considered. So if the SNR is good, no problem. If the SNR is low, then your envelope detector will become worse. So obviously it leads to consider the second situation, that is large noise power. The noise power is higher than the signal power. Okay, again you see the motivation is the same. Okay, so you somehow simplify the envelope expression and then you try to find out at what condition the envelope detector works nicely. So the large noise condition, that means what? The noise power Ni is greater than signal power Si. So we will consider both the situations. Okay, what do I mean by noise power here? Ni is greater than Si. That means what? The signal strength Ni of t is greater than A plus M of t. Okay, so what we are saying is the opposite of what we have said earlier. That is, the noise amplitude most of the time is much greater than A plus M of t. So you put for all time t. And what is this guy? This guy is the received signal part. And what is this guy? Received noise. If you recall, you have noise N of t, and then this is given to band pass filter, and the output of the band pass filter is given to envelope detector. So in this point you have Ni of t. This Ni of t is the narrow band Gaussian noise, and this one is white Gaussian noise. Now our assumption is the received signal is much weaker than the noise, which essentially would imply that Ni of t is much greater than A plus M of t. So this Ni of t contains Nc of t cos omega ct plus Ns of t sin omega ct in terms of quadrature representation. Therefore this expression becomes Nc of t is much greater than A plus M of t, and then Ns of t also much greater than A plus M of t for all time. Now what can you say about the envelope? We already calculated the envelope. What is the envelope? E of t, Ei of t, input envelope, is equal to square root of A plus m of t plus nc of t the whole squared plus n squared of t. Okay, so this component will be higher than this component because you are adding something here. Okay, so here you also nc of t and ns of t, but nc of t plus something and whole squared. Therefore, this you can avoid. A plus m of t plus nc of t whole squared. A plus b plus c the whole square. So that is equal to a square plus b square plus. I'm sorry, because this is large. No, how can you remove that? I'm very sorry. I'm sorry. Wrongly I told you, because this is a larger component, you cannot disregard, right? So you need to consider this guy also and this guy also, because this is much larger than a plus m of t, so you cannot. So therefore let me expand this a plus m of t plus nc of t. So that will be, we know the formula, right? A plus b plus c the whole squared is equal to a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ca. So let us use that formula. So it is going to be a squared of t plus m squared of t plus nc squared of t plus 2ab 2 times a times m of t plus 2bc 2 times m of t nc of t plus 2ca 2 times a times nc of t plus n square of t. That's it. Okay, so what are the terms which are significant here? We said this a is smaller, right? What is our assumption? A plus m of t is much less than nc of t, much less than ns of t. Therefore I can disregard this a term, m square I can avoid, and that's it, right? That's all. So remaining terms will exist. Okay, so you take this term 2c square and n square, so you can write nc squared of t plus n square of t plus 2 times see here also nc and here also nc, you can take nc of t commonly outside, then within a bracket you have 2 plus a plus m of t, right? And any other terms we left. And what about this term 2 times a plus m of t? That also very small, because a plus m of t is less than nc of t, so this also can be neglected. Okay, so this is my final expression. Now this is my ei of t under large noise condition envelope. Now let me consider these two terms, nc square of t plus n square of t. What is that? This is the envelope of the noise process itself alone. Noise process. Because the noise is nc of t times cos omega ct. If you look at here, see, nc of t plus cos omega ct plus ns of t times sin omega ct. So envelope of this is nc square of t plus n square of t whole square root. So therefore the inside this term, this guy indicates the envelope of the noise component. Therefore let me denote this guy as En of t, noise component En of t. So I can rewrite this equation as follows. So En square of t is equal to, look at here, what is this is my envelope. So this I can write as En of t. So this implies En square of t is equal to nc square of t plus n square of t. Square root of nc square of t plus n square of t is equal to En of t, envelope of the noise. Envelope of the noise. Again, if you take square on both sides, then En square of t is equal to nc square of t plus n square of t. Okay. Therefore, you can write this as En square of t plus 2 times n suffix t of t within a bracket a plus m of t. Now you can take En square commonly outside, then it is square root of 1 plus 2 nc of t times a plus m of t whole divided by what? En square of t. Okay. Now if you bring it outside En square, it becomes En only, not En square. So let me delete this. Therefore this is En of t multiplied by 1 plus, let me rewrite this term, 2 times a of a plus m of t multiplied by nc of t divided by En square of t. Now let us look at this quantity. What is it? Okay, because this En square of t is a large quantity, so consider this ratio nc of t by En square of t, and from the normal trigonometric, this ratio can be expressed in the triangle, like because the components are orthogonal. nc of t is orthogonal to ns of t. Both are in phase component and quadrature component. Both are separated by 90 degrees. So let me represent my in phase component by nc of t like this, and the quadrature component will be 90 degree like this, ns of t. Okay. Therefore this is my envelope, En of t. En of t is equal to square root of nc square of t plus n square of t, and this angle is theta n, theta suffix n of t. Therefore what is my cos of theta n of t? This is nc of t divided by En of t. Okay. Therefore this expression becomes En of t square root of 1 plus 2 times a plus m of t times n suffix t of t divided by En of t times 1 by En of t. Now this I can replace by cos of theta n of t. So this is e suffix n of t square root of 1 plus 2 times a plus m of t, then cos of theta n of t times divided by En of t. So that's the expression of your envelope of the signal input to the demodulator. I mean envelope to the envelope which is given to the envelope detector. Once again we can use the approximation here. What is approximation? We said a plus m of t is much less than nc of t comma ns of t, comma, there is a comma. I mean a plus m of t, which implies much less than your envelope en of t. So once again use the approximation using binomial expression. So this, by using binomial theorem, then this is approximately written as en of t multiplied by 1 plus, see this whole thing I can put 1 by 2 and expand using a series, and then you will get a plus m of t by 2. I am disregarding the higher order terms. Then en of t cos theta n of t. Okay, already I have 2 here, the 2 let me put here. So 2 will get cancelled, plus you have many terms, okay, it goes up to infinite series. So I am not considering those higher order terms. So this is equal to en of t, you multiply inside, this 2 and that 2 will get cancelled, plus, and this en of t and that en of t will get cancelled. So you will get I am writing the final answer. You bring this inside and here and here. So a plus m of t the whole thing is multiplied by cos of theta n of t. This is my input to the envelope detector. So this is the final expression. Let me call this expression as A. So this is the instantaneous. What is A of t? Instantaneous envelope. Which means your envelope detector will produce this kind of output. Okay, En of t plus A plus m of t times cos theta n of t. So what do you like to see at the output? You like to see something which is proportional to m of t. But unfortunately in this expression you don't find any term which is a constant times m of t. See, the m of t is multiplied by a noise phase. So it is not even that we have something constant times m of t plus something. Okay, so this amplitude is a constant, but again this is added with the noise component. Therefore I don't get a purely a message signal. So what you get at the output is almost entirely noise, because this is the noise En of t, this is the noise envelope, and which is very large in fact. So nothing can be done with this signal, with this expression, right? So this is also noise, and this is also noise, right? So we will be in trouble. Therefore this noise is, this message is getting multiplied by the noise component, so that multiplication does not help, because m of t times cos theta n is still noise. The message signal m of t, which is multiplied by noisy waveform, and once you multiply a noisy waveform with the message waveform, then it will be still a noisy waveform. So this is not even a signal plus noise kind of expression. If you have like that, okay, somehow you can get back, but it is multiplication of the noise by the message. So essentially the envelope is almost totally noise. The envelope is almost totally noisy, with no component which you can consider as being proportional to m of t, right? So there is no proportional to m of t. Like this situation, it is not at all there. So what does it mean? It means that under large noise conditions, the envelope detector fails to deliver the signal of interest. Therefore it completely breaks down. Under large noise condition. So how do you compare the synchronous detector under large noise conditions? In synchronous detector we had S0 by N0 is equal to m square bar divided by m square bar plus a square times gamma. Okay, so in synchronous detector, when we derived the output SNR expression, we did not have to make any assumption like this, whether in the synchronous detector we did not do any assumption like a plus m of t is greater than ni of t, or a plus m of t is much less than n of t. We did not do this kind of assumptions for the synchronous demodulation. Whether the signal is small or large, you always get this kind of output. Okay, this expression is valid for all conditions of signals and noise. Please remember that. But in the envelope detector, if the noise level is larger than the signal level, then your envelope detector completely breaks down. Now let us plot the output SNR versus gamma, where gamma is the input SNR. That is our benchmark. This is my gamma output SNR. If you remember, gamma is Si by Nb. The SNR at the input is the message bandwidth. So the output SNR is a straight line with a slope given by this equation. What is the slope here? This S0 by N0 is equal to some slope times gamma. What is the slope? The slope is this guy. Therefore, you got an expression like this. Okay, so output SNR versus gamma, you get a straight line. And what is the slope of this line? This is m square bar divided by a square plus m square bar. Therefore, the output SNR is a straight line with the slope m square bar divided by a square plus m square bar. This is for synchronous demodulator. Synchronous demodulator. So it is a constant slope and it will pass through the origin. Okay, it is a straight line curve. So what does it show? When the input SNR falls down, it comes like this. That is, when noise becomes large, the output SNR also falling down. That is bound to happen, right? If something is falling down, if your input SNR is falling down, then automatically that you expect the output also to fall down. So nothing we can do about that, right? So as the input SNR falls down, output SNR also falls down. So that is bound to happen. Now this is for my synchronous demodulator. So the reduction is graceful reduction. Output, when the input SNR is coming down, the output SNR is also coming down, but in the manner of graceful reduction. Okay, now what will happen if you take an envelope detector? In the case of as an envelope detector at high SNR, that means when the signal power is much higher than the noise power, then no problem. It will also follows like this. The moment you cross certain threshold point, then what happens? The input SNR is very low. So let's say in this range you say this noise power Ni of t is much greater than a plus m of t. Okay, then it will not come like this, but it will breaks down. It will break down like this, at low SNR. So this line indicates envelope detector. Okay, we know that high SNR input signal is much stronger than the noise. So under high SNR, I mean in this region, high SNR, okay, high output SNR, high SNR, the degradation will be a straight line like this. Okay, so therefore under high SNR we are more or less on the same curve which we had for your synchronous demodulator. See, this is my synchronous demodulator, right? So in the high SNR, your envelope detector also works like a synchronous demodulator. That's what we derived in this lecture. Previously we derived. See, so in the high output SNR, this is what we got output SNR. So synchronous demodulator also we got this expression gamma, and here also we got the same expression. But at the moment you go to low SNR, then the noise dominates, and the line will not be a straight line. It will be a non-linear line. Okay, so the moment you fall below a certain input signal to noise ratio gamma, the input signal becomes weaker than some value, right? So when the input SNR falls below some value, let's say this value, this point, then you are deviating from the straight line curve. You are start moving down. So this is the synchronous demodulator. Now if you use low SNR region, it comes like this. Sorry, high SNR. So this is for high SNR. So in high SNR region, your performance is close to the synchronous demodulator. The moment you cross certain point, then what happens? Instead of following the straight line, it tries to fall down like this. Okay, you start moving down. Now maybe you move down like this. It is not a straight line. Instead of going the straight line, it comes like this, like that. This is for low SNR. So eventually at low input SNR, you get a signal which does not resemble with your message signal, because the output does not resemble the input at all in terms of the message. So you will get a curve like this. Like this, you will get a curve like that. Now the SNR is a positive quantity, right? Then why should we get the negative axis also here? Because when you plot SNR in decibels, then you can have a negative dB also, right? So you can have negative dB value as well as positive dB value. Okay, if you don't plot this SNR in dB, then we could have only positive x-axis and positive y-axis. So when SNR is less than 1, then you will get a negative SNR in decibels. So let me draw one more figure. So this is important. This is S0 by N0, and this is gamma, and you have a straight line. Now the envelope detector will come like this, like that. This is for envelope detector, and the straight line is for synchronous demodulator. So this kind of phenomenon that is exhibited by the envelope detector is called threshold effect. So at certain point it deviates. So this point is called a threshold point. So therefore you should always operate your envelope detector above the threshold value. Okay, so the threshold effect says that the output SNR does not degrade gracefully. See, here it should supposed to come like this, but it is coming down like this. Therefore there is no graceful degradation. Okay, as the input is reduced up to the threshold point. So when the input SNR falls below the threshold point, you will find that the output SNR degrades much more rapidly. It is shown in the pink color, sorry, violet color. So you will find that the output SNR degrades much more rapidly. If the input SNR degrades the same amount, then if the output SNR also degrades by the same amount, then it would have been a straight line, but it degrades the output SNR degrades much more, and therefore there is a concept called threshold value of the input SNR. You must always operate above the threshold value, because if your receiver is operated below the threshold value, you will get a very bad and highly deteriorated output, which will not resemble the signal at all. Fortunately, this particular effect is not that much important, okay, in a typical broadcast applications, at least in amplitude modulation. The reason is the value of the threshold at which this happens, okay, is of the order of 10 dB actually. This is something 10 dB generally. That means unless my input SNR falls below 10 dB, I will continue to be more or less in this linear region. Okay, in this linear region. If my input falls below 10 dB, then I should worry. So a typical acceptable value of SNR in the broadcast application is anyway between much larger than 30 dB. In commercial applications, your threshold, your gamma typical will be much greater than 30 dB. So in AM system, no need to worry much about threshold value. Okay, so gamma threshold is 10 dB, but generally in our typical commercial applications, I will always get a gamma value will be greater than 30 dB. Commercial applications, this gamma benchmark is always greater than 30 dB, right? So since the typical values are going to be much larger than the threshold value, we never see the threshold effect in typical AM radio receivers, typical AM demodulators, because you are typically operating at input SNRs which are much larger than the threshold value. See, the threshold value is roughly around 10 dB, but in commercial applications your SNR will be, input SNR will be around 30 dB. So the threshold effect never occurs in AM system. Okay, now what are the motivations to use an envelope detector? Because it has threshold effect, right? In your synchronous demodulator, we don't have this threshold effect and all. Even if the signal goes bad, then you can recover back, not a problem. But here, if the signal input SNR goes below a threshold value, then there is some problem. Then what is the reason, or why do we need to use this envelope detector? Because of its simplicity. Okay, so your envelope detector is much a simple circuit. Therefore, the envelope detector is mostly used to capture the information without much loss. So that is the lesson that we have learnt from this. Now the next question one should ask is, how can I calculate this threshold value? Okay, so that is the next topic of interest. So we need to calculate gamma threshold. That we will address in the next class. So let me stop at this point.